We're looking at homework 6. Which problem were we talking about?
It's number 5.
Homework 6, problem 5. Can I take a look at it? So homework 6, problem 5 states, in the presence of excess NH3, qualitatively describe how much uncomplex nickel ion remains in solution at equilibrium. Explain. So, whoa, that's a really vague question. So we have to think about this. We've got NH3. We've got nickel 2 plus. What are the possible things that could happen? Keep in mind, this is homework 6, chapter 19. So what's probably going to happen? It's probably going to form a metal complex. Probably going to form some nickel NH3 complex. It's going to be in the +2 state. And we're going to need some value there for how much for how many ligands are on this nickel complex. We're also going to need a KF for this. But even without a KF, even without looking up the specific value for this, what do we know about almost every metal complex? I know it's 6 because I looked it up. Remember, nickel is one of the ones that has the possibility of going square planar, but can also go to octahedral. It's one of those exceptions that could do a weird thing or could just be octahedral like most things. With the ammonia, and we have to still figure out what ligands cause these different geometries in addition to what metal centers can have the different geometries. But nickel does this. What do we know about the formation constants for most of our metal complexes? They're going to be large numbers. They're going to be much greater than 1, right? They're going to be big numbers. In that case, without even looking this up, without even knowing that if it was NH3,4 or NH3,6, which way is this equilibrium going to lie? I've got my double arrow. Towards products. But it's going to essentially be all products. Because the KF, and if you actually go and look up the KF, according to the textbook I just looked in, 2.0 times 10 to the +8. I'm thinking that's a million. It's 100 million times more products than reactants. So, how much nickel are we going to have left in solution?
Not a lot.
Very little bit. We can just qualitatively tell that without having to do a calculation. Now, if we wanted to, we could also do a full calculation. We could look at this and say, since the KF is large, I'm going to do stoichiometry, and then I'm going to do an equilibrium back to see how much nickel is left in solution. But in order to do that, we would also need a volume of solution, a concentration of each thing. We need some way where we could get the moles of each thing in order to make that happen. And the problem doesn't give us that. It just asks us to qualitatively describe what we think will happen. Most formation constants are giant. The smallest formation, just for sake of argument, the smallest formation constant I can find is 1 times 10 to the -6. This is a list of 20 or so different formation constants in this textbook. And the smallest one is 10 to the +6. 1 million times more products than reactants. Now, we also wanted to look at homework 6, problem 2.
Yeah.
Okay. This one, like I mentioned before the video was running, is actually a 127 review problem. Right now, in my 124 class, we are just getting to the carbonates lab, and they're just doing this calculation. And I thought, hey, won't it be interesting to see if 129 students can still do the carbonates calculation with a little bit of a 129 twist. So this is really just a stoichiometry problem. There's not really any equilibrium phenomena or anything like that we're looking at. It's just a stoichiometry problem. It is a competitive solubility to some degree, but it's going to be stoichiometry dominated. So what are the materials? So we've got NaCl and KCl. They are going to react with AgNO3. Yes? And that's going to form AgCl plus KNO3 and NaNO3. And the problem is, these two things are mixed up. So I can't really tell how much of my Cl comes from the sodium chloride and how much of my Cl comes from the potassium chloride. There are a couple things I know, though. What are the things we know?
We know the weight of the precipitate at the end.
What is it?
8.5904 grams.
Okay, what else do we know?
You know that your cell mixture that you start with is 4 grams.
What else do we know?
That's about it. I mean, they're aqueous.
We don't know how much silver we're adding?
It just says excess.
Oh, excess. Great. That's important. Right? That means the silver is not going to be the limiting reactant. The chloride is going to be the limiting reactant. That's important to know. So when we look at our stoichiometry, we know that we're going to have 4 grams. And that's going to be X grams of NaCl plus Y grams of KCl.
So is the AgCl the thing that is the precipitate then?
Yeah, so the AgCl is the precipitate.
Right.
And I know how many moles of AgCl I have. Right? So I can take my 8.5904 grams. I can multiply by the 1 over the molecular weight. What's the molecular weight of AgCl? Periodic tables. Or internet. That works too.
143.35.
What is it?
143.35.
Now, this will give us the moles of silver chloride, and then I can multiply by the fact that these are both 1-to-1 ratios. To get how many moles of chloride ions we have. Homework 6, problem 2. I cannot do that in my head today.
I like 0.0599.
That gives us our moles of chlorine minus. The catch is, I know my moles of chlorine minus come from my grams of sodium chloride and my grams of potassium chloride, but I don't know how much of each I have. What I can do, though, is if I take my X grams of sodium chloride and I multiply by 1 mole sodium chloride, what's the molecular weight of sodium chloride? 48? 58? 58. I need a periodic
58
table.
seems right.
58.44.
58.44 grams times 1 mole Cl minus for 1 mole NaCl. Notice this calculation will give me moles of chloride ions from the sodium. That's not my only source of chloride ions, though. So then I need to add to that my Y grams of not NaCl again. KCl times the mole rate times the molecular weight times the 1-to-1 mole ratio. I don't know KCl's molecular weight. I really should, shouldn't I? 75. It's right below sodium.
74.5.
Oh, so wrong. 74.55.
55.
So notice, in this equation, I've got chloride ions plus chloride ions is going to give me my total amount of chloride ions. So I'm using the fact that I had a known amount of silver to get how many chloride ions I reacted with. And I'm using the fact that this was the limiting reactant because the silver was in excess to get an equation that should be equal to this. I'm going to rewrite this in a more visible color that just gets to the mathematics. X times 1 over 58.44 times 1 over 1 plus y times 1 over 74.55 times 1 over 1 is equal to 0.0599. What this says is the chlorine ions from the sodium chloride plus the chlorine ions from the potassium chloride has to be equal to my total amount of chlorine ions because it's the limiting reactant. You'll notice this equation has an x and a y, so we've got two unknowns. And we can't solve one equation with two unknowns, but we also know 4 equals x plus y. Now we've got two equations and two unknowns. Can we substitute and solve? I need more violent yes nodding. Yes, we can substitute and solve. One of the mathematical mistakes that people make when they're solving this is we can simplify this expression a little bit, right? We don't need the one to, if we're just doing the math, we need the 1-to-1 ratio for the chemistry, but not for the math. So we can get rid of the 1-to-1 ratios. That simplifies things a little bit. I don't need to keep that as an individual fraction. I can just put 1x over 58.44 plus y over 74.55 equals 0.0599. The mistake that most people make when they are solving this is they look at 58.44 and they look at 74.55 and they go, ooh, what's the common factor? Right? That's how we deal with fractions. We find the common factor. That's going to be an ugly common factor. Really ugly. Here's my suggestion. What's 1 divided by 58.44? In your calculator, not in your head.
0.017.
So we're going to take this and we're just going to say 0.017. Give me one more digit on there.
1.
What's 1 divided by 74.55?
0.0134.
That becomes a lot easier to deal with, right? Getting rid of the fractions, just turning them into decimals. The most common place where students make mistakes on this is just dealing with those weird fractions and not realizing that we can just convert them to decimals and then do the math. Next thing we have to do is substitute in, do we want to solve for x first or y first? Let's solve for x first. That means I'm going to have 4 minus x equals y, so I'm going to take this. I'm going to come over here. I'm going to have 0.0171x plus 0.0134 times 4 minus x is equal to 0.0599. At this point, it's just algebra. And I will let you do the algebra on your own and come up with the value for x. Let me know when you have a value for x. Oh, no, we'll be okay.
$1.702 to 1.702.
We got one agreement. Now there's three agreements. Okay, x equals 1.703. What are the units on x?
Grams.
Of?
Um,
Yeah, so we also have to keep track of what we're doing here. Because of the way we set up the problem, there's a completely different way to set up this problem, where you make your moles your unknown variable, and you solve for the amount of moles rather than the amount of grams. But because of the way we set this up, where our total grams was equal to our x grams plus y grams, our x and y are going to be in grams of their different components. All of the mole ratios and the molecular masses, those all took care of the units for us. And so we get something that's in grams of sodium chloride. We can use that x grams in our equation in green. That's 4 grams equals x plus y. We can solve for y. It's going to be like 2.3. Notice the question asks for percent by weight. If you've got about 2 out of the 4 grams is potassium chloride, it's about 50%. It's a little bit more than 50% because it's 2.3. If you've got 1.7 grams out of the 4 grams is sodium chloride, it's going to be like a little less than 50%. Probably a 60-40 mix. And that's all. You notice in this, we don't have any equilibria. We don't have any precipitation. We kind of got rid of the competing precipitation. We were really only making one precipitate. And sodium chloride, potassium chloride are both soluble in water. So that's not really going to have an effect. Since the silver was in excess, we're not really going to have an equilibrium issue because there's plenty of silver. We're not going to run out of silver. You could argue that if we did this stoichiometry, we'd end up with 0 chloride in solution, and we know that shouldn't happen. So we should go back and correct for that. But again, that's, since this is just asking how much of each in the original mixture, it's really just a stoichiometry problem. Also, the KSP for silver chloride is on the order of what, 10 to the minus 12? It's small. So the redissolve is negligible. It's not significant. It's not pertinent to the question either.
Also, off topic from this, but what is a Lewis adduct?
A Lewis adduct is when you have a Lewis acid base producing one compound. So that's a lot of our metal complexes where you have a metal center acting like a Lewis acid. You have some ligand acting like a Lewis base. They combine to make one thing. When you're adding 2 things together, you make a Lewis adduct. I'm assuming you're all doing the vocabulary in the back of the chapter. Yeah, all quarter I've been assuming you've been reading along with the textbook, doing the vocabulary in the back of the chapter, doing the extra problems for fun, for quote unquote fun. With all your free time, it's like bored on a Friday night, get your friends together and do some chemistry problems.
It's my favorite thing to do.
Other questions?
I know that it's a review from way earlier, but could you maybe do one of just as an example for the molar solubility problem on here? Just
that
those examples.
Problem 8.
Problem 8. So maybe D or something. It's saying in 600 milliliters of a given molarity solution.
Well, D is the only one that's tricky and new.
Yeah.
Let's just think about. Let's look at the other one. So this is. Okay. Homework 6, problem 8. Yeah. We did that yesterday in office hours as well, but repetition is the key to learning, so let's do it again.
Is it online?
Yeah, but let's do it again. Let's do it again. We'll do it a little bit different, and maybe it'll be better this time. Homework 6, problem 8. We're looking at silver iodide, if I remember correctly.
Mm-hmm.
And we're looking at it dissolved into Ag plus I minus, where, again, we finally have to be careful with states of matter. So this is what we've got. We have solid dissolving into two things. If we just wanted to do this in water, we start with zeros there. We just do our standard KSP equals x squared. Do we know the KSP for silver iodide? I just looked it up. In the textbook, we get the value of 8.3 times 10 to the minus 17 is equal to x squared. We take the square root of that. That gives us our molar solubility, which is going to be something like 3.2 times 10 to the, oh no, I'm totally off. Odd exponents always mess me up. It's going to be like 4.7 times 10 to the minus 9 or 8. Calculators, help.
You want to get some from the
Let me do something for you real quick. Do you know the trick here? So you go
This is so much better. Something's off. Okay, cool.
I could tell you had the little like swoop
Yeah,
marks on your
it always
calculator.
happens, and I'm like, why?
Let me see this. So there's this thing you can do with your calculators, where if you hit second scientific, you can switch between flow, which just puts it all out of zeros, and you notice it truncates your digits, so you just get 0.00000009, which is not significant enough. And if you hit second, you hit the science engineering button, you can go to scientific notation, 9.11 times 10 to the minus 9, and you won't get those swoop marks on the bottom of your calculator.
Wow.
So that gives us 9.11 times 10 to the minus 9. Man, I cannot do square roots in my head sometimes. So that is the solubility. This is going to be in molarity. That's the molar solubility of silver iodide just in water. That's part A. What do we do in part B?
It's in water with a pH of 3, so.
Ooh, pH of 3, acidic conditions. What will acid do to the solubility? Nothing? Not change it?
You're pressuring. Not changing.
Not change it. We're just going to agree with everybody else. It's not going to change it. Why isn't it going to change it? So if we look at this, we have H plus, will be technically correct, H3O plus, right? And we say, okay, it's not going to interact with another cation, so it can only interact with an anion. That would make HI, hydroiodic acid. And we know that if the anion of a solid is the conjugate base of a strong acid, a decrease in pH will not affect the solubility. If the anion of our solid is the conjugate base of a strong acid, a decrease in pH will not change the solubility. We usually set it the other way, where we would say if the anion of the solid is the conjugate base of a weak acid, a decrease in pH will change the solubility. So we're just looking at the anion saying, is it strong acid conjugate or a weak acid conjugate? In this case, it's a strong acid conjugate, no effect. Your solubility is going to be the same value. Part C.
So I like looked up all
0.5 moles of Na. NaL?
I think it's NaI, sodium
Oh,
iodide.
yeah, my bad.
And is it 0.5 capital M, 0.5 molarity? So if we look at this, all we're going to change in our equilibrium is we're going to essentially have the common ion effect. We're going to have a 0.5 molarity here for our I minus. And we're going to end up with a similar calculation. 8.3 times 10 to the minus 17 is equal to 0.5x. 8.3 times 10 to the minus 17 divided by 0.5 would be 1.66 times 10 to the minus 16. Double check me. I just multiplied by 2 and I don't know if I did it right. Because dividing by half is like multiplying by 2. You need a nap, huh? Yeah.
Also, I lost my calculator, so.
Oh, bummer. No calculator on your phone?
I do have one on my phone, but I don't know how to make it to like.
Let's see which one you have on your phone.
It's a horizontal, yeah.
Oh, wait, it's a controller.
You have to like reopen it. It's really weird.
God.
But like the settings there are really weird. You have to like push your numbers in and then like do your other stuff. You can slide it up and then go back to your calculator again. I'm pretty sure.
Oh, yeah.
There you go. All your calculation needs. Is this what we get?
The buttons and the numbers and then like.
Oh, and
really
then the,
weird,
like
yeah.
function.
So, notice common ion effect dramatically decreases our solubility. We go from a solubility of 9.11 times 10 to the minus 9, which is not soluble, to a 1.66 times 10 to the minus 16, which is really, really, really not soluble. We have a dramatic decrease in our solubility when we have the common ion effect. Now, the last one is the one that is most tricky. Part D is the one that's new. Right? In this case, we're adding NH3? Question mark? Yes?
And I see.
Oh, sodium cyanide. Sorry, I was thinking of the last problem. So we're adding NaCN, and we've got 600 milliliters at what concentration?
0.911.
Now this already gives us a clue, right? And we want to start thinking about the clues that are given to us in the problems when we read them. There's entirely the possibility that it's a red herring and I'm giving you the volume for no reason. But there's also the possibility that I'm giving you the volume so you can get a number of moles of cyanide. And if you can get a number of moles of cyanide, you probably need to do some stoichiometry. There's another reason why we can think about the need to do stoichiometry. If we think about what's going to happen in this case, we're going to have AgI plus NaCN. There's another clue in the problem, right? Before I get too far ahead of myself. What's the other clue?
It gives you the KF for.
And what's the KF tell us?
It's KF for AgCN2 and 1% of the 21st.
So there's another clue given. Again, I could be a jerk. I could be giving you the I could be giving you the KF and the volume just to try and trick you. But I don't really like to do that. I try not to do that. The place where you didn't need it for A, B, and C, but you needed it at part D. I also, if I gave you the KF at the beginning, you don't need the KF until the end. But, you know, it's still eventually you needed it. Here I just gave you both the parts right at the end. And we actually need both those parts. Those are both clues for us. The fact that we have a KF means that we're going to forming a metal complex. And notice we've got the solubility reaction versus the metal complex reaction. If I look at my solubility, let's do it this way. Which direction is this solubility going? I'm trying to calculate my K overall. Is the solubility going in the normal direction we write solubilities, or is it going backwards? Normal, right? We always write solubility as solid, breaking apart to ions. So I'm just going to have KSP. Now, is my formation reaction going in the forward direction or the reverse direction? Again, here we have to remember that the formation reaction is always for the creation of the metal complex. So both of these are going forward, which means we're just going to end up with KSP times KF. We looked up the KSP, 8.3 times 10 to the minus 17. The KF was given. We can calculate the K overall.
So for test one, I just do this. So add one probably.
Isn't that great? 8.3 times 10 to the 4. Agreements? Great. So we're going to go ahead. I'm going to erase this stuff in orange and just write the K reaction. I use K reaction, K overall, K total kind of interchangeably. 8.3 times 10 to the 4. I'm going to put that plus sign there because I want to make sure that we're not just forgetting that it's positive. This is actually supposed to be a positive 4. Now, what does that 8.3 times 10 to the positive 4 tell us?
We'll be forming a lot of metal complex and ions.
Yeah, and destroying most of our solid. Now, in this situation, you can imagine we've got a big old beaker of 600 milliliters of this sodium cyanide. I didn't need that minus there. And I'm just putting spoonfuls of silver iodide in until I see them stop dissolving. So essentially, this process says the AGI is going to be excess. I get to pick how much I put in. And really, it's going to be the thing I'm solving for. I want to know how much I can add in order to get to the correct point. Now, my sodium cyanide, I have 0.6 times 0.91, my volume in liters times my molarity. That will give me my moles of sodium cyanide. And I've got zeros of these. Notice, because I've got 0 metal complex and 0 iodide, I could not write this reaction backwards. Okay? I couldn't do this backwards. I have to have reactants in order for a reaction to happen. If I tried to do this backwards, I'm adding zeros together. It doesn't work. I have to do this reaction this way. 6 times 0.91 should be something 0.5-ish. 90% of 0.6 is like 0.5, probably 0.55, 0.54.
0.55.
Oh. 0.55. Is there another digit on there? Yeah, close enough.
It was 0.545.
54555. Close enough. Notice, because this thing is kind of the excess, I know that this sodium cyanide is going to be the limiting reactant, minus 0.55, minus 0.55, plus 0.55, plus 0.55. We have to be careful and remember our mole ratios because we're not doing buffers anymore. We've actually got mole ratios. It's not all 1-to-1. So I'm going to have a 1-to-2, 2-to-2, a 1-to-2, and a 1-to-2. The reason we know this is because the limiting reactant molar coefficient is always on bottom. if this is actually the limiting reactant, that's going to be 0. 0.55 divided by 2 is 275. This is a little bit different from our answer yesterday because we rounded a little bit extra today, but close enough. And you notice if we are at the exact solubility saturation point, that's also going to be 0. If we hit the exact point, we're not going to quite have excess. We're going to have equal molar. That means that the amount of silver iodide that can dissolve is also going to be 0.275 molarity, which makes sense because the only source for silver is the silver iodide. So it makes sense that these two would have the same concentration at saturation. The ions, the number of ions in the metal complex should be equal to the number of ions that we lost from the solid dissolving. This is going to be our apparent solubility. But wait, can we actually have zeros here? Do we need to do a correction? Technically, yes, right? We need to do the correction. But what's the K reverse for this? If we say, okay, now that I've got these reactants, I can establish my equilibrium backwards, like we always did with our solubilities. Give myself a little bit more space. I can look at my K reverse, which is just going to be 1 over K reaction.
How did you get a 0 for, why did the AGI, like, column there?
That was if we're at, it's if we're, oh, you can't read that at all. So this says, if at equal molar. Yeah, so if we're at the equal molar point, that is to say where both of these are limited, right? I added just the right amount since we've got our bucket of sodium cyanide and we're adding as much silver iodide as we want. We added just the right amount to where no precipitate was forming. There was no solid left in solution.
Okay.
So it's kind of theoretical.
It's 0.55.
Exactly, yeah.
Would those values that we get, wouldn't they be in moles though, because it's a SRE table? Or
Oh, you are totally right. You are right, you are right. These are moles. So we should go back and divide by 0.6 to get the molarity. What's the K reverse? Sorry, question before I get to that.
So how big should the K value be for us to think that we need to do the stoichiometry table before jumping dice? I know if K is or X is small.
Anything over 10.
Anything over 10? Okay.
Right, anything over 10, you're going, well, really anything over 100, anything over 500. You know, it's like anything in the 100 to 0.1 range, our approximations are probably going to be bad. Anything beyond that, the approximations are probably going to be pretty good. And, you know, it's one of those things where it's like, well, how accurate do you want to be? Technically, you should never make an approximation if you want it to be accurate. Who's got time for that? What's the K reverse? I don't know what 1/8 is.
(1.2 times 10 to the -5).
Here's what I want to ask. Before
Sorry, you got that by doing,
1 over K reaction.
oh, 1 over K reaction.
Yeah, just flipping the reaction. That's for the reverse of this reaction. So we can consider, do we need to worry about the reformation of the solid, the redissolving of the metal complex for the reverse reaction to affect our molar solubility? Is X going to be small with 1.2 times 10 to the -5? Yeah, X is small. We can probably ignore the equilibrium table. Problem D is completely stoichiometry dominated. Now, we could add an extra question to this to make it a little more tricky, to force you to do the equilibrium table. I could say how much cyanide ion is left in solution at equilibrium, right? And then that 0 is going to be some really small number, probably on the order of 10 to the minus 5, 10 to the minus 4. But you would actually have to do the ice table in order to answer that.
Wait, though, so for actually answering just straight up what is the molar solubility in this situation for AgCl, is that
It's going to be 2.75 divided by our total volume, which is 600 milliliters, or 0.6 liters. And that should be the molar solubility. Notice this is a really fantastic problem. It brings back some of the solubility stuff. Fantastic is relative, I know. But it brings back some of the solubility thinking that we had at the beginning of the quarter. And it gets us thinking about what does it mean to have molar solubility versus saturation. And it also brings in the metal complex idea of how another way we can influence and manipulate solubility of different ions. It's also something you practically have done. Like you have done this in lab. You didn't do it with cyanide because it's a little dangerous, but you did it with ammonia. See ya? Where you dissolved your silver chloride, but not your silver iodide, based on the KFs versus the KSPs for those different materials. We did this in lab for the for the chlorine test.
Yeah. So the reactants, kind of depending on the reactants, it'll force us to solve in one direction or another if we only have
Yeah, right. Because you have to have reactants present for a reaction to happen. It was the same thing we saw in buffers, where in the buffer range we got to pick which direction the reaction went because we had all the reactants and all the products present.
Yeah.
At the equivalence point, we had to go a particular direction because we only had one possible reactant present.
Yeah. Thank you.
See ya. Other questions? You just want to know about lab? Other questions?
I had a lab question.
I think I'm going to stop the video for now. And we can start it up again if we need to. No one watched. See ya.